welcome everyone to the Wilson Forum today. I'm really delighted that our speaker is someone I've known for actually a few years now. Amit Goyal is a professor at the State University of New York in Buffalo. He and I were colleagues in a National Academies committee, which was given the task of evaluating the progress that the National Science Foundation had made in moving forward with the nation's agenda for the Materials Genome Initiative. And that took us almost a year and a half, something like that. So I got to know this guy pretty well. He's not only a distinguished academic and an inventor and innovator, but he's a darn nice guy to work with. And Amit, I enjoyed our interactions as a member of the National Academies Committee. Today, we're welcoming you to the Wilson Forum. We're looking forward to hearing your comments about high-temperature superconductors. So, Amit, the floor is yours, and welcome to the Wilson Forum.
Thank you, Ron. Thank you for the nice words and for the invitation to speak at this nice forum. Let me see if I can share my screen. Can you see my screen?
I can almost. We see a Zoom symbol.
Yeah, so I will get my PowerPoint up.
There you go. There you go. Perfect.
Wow.
See it?
Yep.
Let me just
There you go.
downsize everything. And okay. So thank you again for the invitation to speak. I'm going to talk about high temperature superconductors, and I'm going to take you on a journey from the discovery of these fantastic materials to large-scale industrial applications. So just to briefly mention, I was at the Oak Ridge National Laboratory for about 25 years. I've been in academia for about 10 years now. And let me get the pointer here as well. Okay. So I have designed this presentation for the non-expert, but also hopefully has enough for the experts to keep hopefully everybody's interest. And I'll get you a grade towards the end, whether or not somebody who does not have a background in this area could understand most of what I was saying. So with that, let me move forward. And okay, so two IBM scientists, Bednorz and Mueller, discovered high-temperature superconductors in 1986. And I'm sure many of you remember that time, because at that point in time, every newspaper and magazine, whether it was a scientific magazine or not, most of them anyway, carried articles about how these materials called high-temperature superconductors would change the way we live. Bednorz and Mueller were awarded the Nobel Prize in 1987 for a discovery made in 1986. First time in the history of science, a Nobel Prize was awarded 1 year after the discovery was reported. They reported a superconductor, and I'll tell you what a superconductor is later on. They reported a superconductor which becomes superconducting at around 40 Kelvin. And for about 100 years since the first discovery of a superconductor in mercury, you see the slope of increasing the temperature at which a material goes superconducting. Suddenly it went all the way up. There was an immense excitement in the field. Professor Paul Chu at Houston first reported a 90 Kelvin superconductor. 90 Kelvin is above liquid nitrogen temperature. The cost of liquid nitrogen, similar to mineral water, created immense excitement around the world. And the Nobel Prize in 1987 was not awarded for the theory of high temperature superconductors. That is still not known. It was partially awarded for the immense potential applications of these fascinating materials. Here's a picture of Bednorz and Mueller. They were obviously quite excited when they heard that they received a Nobel Prize in physics. When this occurred, most scientists, irrespective whether they were in which area of science they were in, If they could work in high-temperature superconductors back then, irrespective of what background in science and engineering, they were doing something in high-temperature superconductors. There were reports of what we called USOs, unidentified superconducting objects, which may become superconducting at room temperature. That still happens. There was only one report of high-temperature, room temperature superconductors that was accurate. And this carried the title, announcing the world's first superconductor that works at room temperature. And this was an announcement in 1989 for a symphony conductor. All right. Now, many of you are familiar with Woodstock, famous music festival, 3 days of peace and music, 1969. The only area in the field of science ever to claim a Woodstock of physics and science is high-temperature superconductors. This occurred in 1987. It is widely viewed as the Woodstock of physics. This is the APS, the American Physical Society meeting held in New York City. And this was the only time when science came on the front page of the New York Times. This was an excerpt from what is happening at the APS meeting. Here's a sort of a blurb from 2019, which is saying the Woodstock of physics is now finally living up to its promise. And you will hear why that headline came in 2019 later on. So there are two main properties of superconductors that one can start with. One is that when you cool the superconductor below a certain temperature on the x-axis, it loses all its resistance. That's what we call a superconductor. If you take a superconducting material and cool it below its transition temperature Tc, it behaves like a perfect diamagnet. And so if you put a permanent magnet over it, it levitates. Based on these two bulk properties of superconductors, you can envision an applications tree for these materials with branches in energy conservation and physics, machinery processing, electric power, energy, transportation, electronics, and communications. I won't go through all of these, except to mention each one of these could be $1 billion alone. Electric power, everything in the electric power grid, from transformers, generators, fault current limiters, transmission cables, everything can be superconducting, become more efficient. MagLev trains you're familiar with, you've heard about them, they're being developed now in earnest in China and Japan. Transmitting power, next generation MRI, next generation NMR for drug discovery, and nuclear fusion. However, for all of these large-scale applications, you need long lengths of superconducting wire that can carry large amounts of current. Imagine you taking a single hair strand from your head and saying that you're going to pass over 1 million amps per unit cross-section of that on that hair strand. That's the kind of performance we need for all of these applications. Just here's another slide showing you applications in energy generation, transmission, storage, energy efficient power devices, medicine, transport, and defense. When you have offshore wind turbines, you cannot increase the mast any longer. If you want to double the power, the only way to do that is to put a superconducting generator. Transmitting power from where it is consumed on the east and the west coast to where it is generated, especially things like wind and solar. Underground transmission cables you're looking at here. This is a case in New York, which is already, this line is already there. You're looking at a MagLev train here. Industrial applications include melting steel using high magnetic fields created by superconducting coils. All of MRIs and NMR magnets are superconducting wires again. And the next generation MRI and NMR are going to be produced using these materials. And of course, then you have space exploration, high energy physics, and all of that. Crystal structures of these materials. These are complicated materials. The so-called 90 Kelvin superconductor is yttrium barium copper oxide. It has copper oxide chains, two-dimensional copper oxide chains, and one-dimensional copper oxide chains and two-dimensional copper oxide planes. It's got an yttrium atom at the center of the unit cell, two barium atoms, and copper at the cube edges. Then there are more complicated materials, which are this is called the BISCO, or the 2223, bismuth, strontium, calcium, copper oxide. You can think of them as charged reservoirs interdispersed with superconducting planes. Higher the TC, you have a greater distance between these superconducting planes. So the 90 Kelvin superconductor looks like, in fact, all of these superconductors look like mud in your flower bed. You can use the most advanced ceramic processing techniques to create beautiful microstructures like this one over here, where you're looking at twin planes along the 110 direction within a grain. Even when you have these beautiful microstructures starting from this mud-like material, when you pass a supercurrent through a material divided by the cross-section area, you only get about 1,000 amps per centimeter squared. And when you apply a magnetic field, where most applications are in high magnetic fields, the current carrying ability drops dramatically. And this happens because of issues at grain boundaries and micro cracks. This is, after all, a ceramic material, a traditional ceramic material. Nevertheless, the excitement worldwide was so fantastic that companies formed in most advanced countries around the world. Many in the US, many in Japan, many in Europe, in Asia. And how did they work? They took the mica-like material that I mentioned to you, mica-like because this was layered structure. So when you deform it, it cleaves like mica. And they put it into a silver tube. Why silver? Because silver was the only known material that did not react with it detrimentally. They put this superconducting powder in a silver tube, extruded it, make a wire, rolled it into a flat tape, heat treated at high temperatures, and created tapes like this. Right there in Boston, where you are, American Superconductor invested $200 million in creating a factory to create these wires. These are their wires, a picture of them that I'm showing you here. These wires quickly became commercial. People made kilometer-long lengths of these materials. In fact, there's a company called Southwire. It is the largest copper wire manufacturer in the United States. When I was at Oak Ridge, we worked with them, and these are three cables, superconducting cables that are placed in Southwire. They were placed in 2001 as a demonstration project for superconducting cables. All the power coming through the plant and being used in the plant goes through these three superconducting cables, and they perform beautifully. However, the performance of this wire used in this application was 50,000 amps per centimeter squared. In order to realize large-scale applications, what we really need is the blue curve. Here you're plotting the amount of current you can carry per unit cross-section in amps per centimeter squared. This is over 1 million starting out at 0 applied magnetic field. And when you apply magnetic field, this is a curve for a single crystal of the superconductor, a film, on a single crystal substrate where all the atoms are aligned. Question is, how can we get such a performance in superconducting wires? If we can, then we can potentially enable all these applications, which was the vision that created all this excitement. So we took those silver tapes that I showed you previously and etched the silver away to reveal the superconductor. Then we used a technique called electron backscatter Kikuchi diffraction, where you put an electron beam at a certain point on the sample, you get a unique electron diffraction pattern. When you index it, you can get the unique orientation at that point. Now, if you were to take 100,000 diffraction patterns in a small area, you can recreate the grain boundary misorientations in this particular image. The green ones are what we call low angle boundaries less than 10 degrees. Red are high angle boundaries. And here it's a much larger image. Basically, we've looked at a whole bunch of grain boundaries here. We find that the current transmission can be explained by percolation through low angle grain boundaries in these bismuth 2223 wires. Well, another superconductor was also making strides. This was being promoted by General Electric. They were developing this. It was called a thallium-1223 wire. It was a thick film, looked something like this, and it carried a little bit higher current than the bismuth wire did. Well, we got interested in it. We were working with GE very closely back then, and we said, well, how is this wire performing better than the bismuth wire? And so we started doing very advanced techniques like micro X-ray diffraction. And when you do X-ray diffraction in a larger spot, you get no crystallographic texture. But when you do it on a smaller beam, 100 microns, this was done at Brookhaven National Laboratory in the synchrotron light source, you find that these peaks show that there is local orientation. So when we step this measurement along a large area, anything which has the same color, you're really looking at the A and the B axis of the superconducting unit cell. Wherever you see these are aligned, all the atoms in those regions are aligned. So you can go one step in greater, a more greater level of detail. Here we are taking from point 0, an electron beam, and we're looking at that electron diffraction pattern that tells us the orientation in space, and we move it in straight lines. Wherever we encounter a change in orientation, we plot the orientation of the A-axis. So here you can see all the A-axis are aligned. Then there are going to be regions where they are not aligned. And here you have an area where there is what we call a colony intersection. There's a high angle grain boundary. And then there are regions where the orientations, A-axis orientations, change gradually. So again, in this material,
just a question. In order for that to be effective, though, the orientation has to be such that there's direct contact between each one in order to produce to allow conductivity, right?
yes, there is direct contact. So now, so basically, in this here we're looking at this is an individual grain from here to here and from here to here.
Right.
So now we're going to call a region of locally aligned grains a colony.
Right.
And here we are saying each one of these areas is one colony of many grains with common A-axis orientation.
Right.
So here we've got a high angle colony boundary. If you were to pass current through here, you will not get current transmission, but you can get percolative current transmission.
Right. That's what I was thinking.
Exactly.
Yeah.
So now the question is, we've got a one-to-one correlation. This is the A-axis orientations in this particular micro bridge that we created. Here is a high angle grain bound colony intersection, and we can actually image the supercurrent, and we find that here the current is low. So now the question is, how do we increase the performance? The only way we can increase the performance is if we get a near single crystal in long lengths.
Right.
Can I just ask how wide is the grain boundary?
So these grains here are a few microns. Each individual grain would be a few microns.
But the boundary itself?
Oh, the boundary itself would be, you can approximate it as let's say you approximate it as a 2 micron in these thallium-1223 wires, a 2 to, it of course is a range of grain boundaries in these materials. Let's say 2 to 10 microns, and you can envision it as approximate it as a circular grain of about 2 to 10 microns. And so, approximately that would be the grain boundary.
So it's not within tunneling dimensions.
I'm sorry?
It's not within tunneling dimensions.
No.
These are microscopic. Okay.
So there was this beautiful experiment done at IBM. They took a strontium titanate bicrystal. Bicrystal is one where you can define the grain boundary misorientation to whatever you like it to be. And then they grew the superconductor, the 90 Kelvin superconductor, atom by atom, such that the atomic structure of the superconductor was replicated, the atomic structure of the strontium titanate was replicated. So now we have created a grain boundary of a certain misorientation in the superconductor, and now you can pass a current through it and plot the amount of current you can pass through this grain boundary intersection divided by the amount of current you can pass within the grain. When you do that and you plot this as a function of misorientation angle, irrespective of the nature of the grain boundary, meaning how the grain boundary is oriented, tilt versus twist, you find that when you go beyond really 5 degrees, the current transmission drops exponentially. So, what do we need? In order to realize the dream of the 1987 Nobel Prize, we needed a kilometer-long flexible single crystal for reducing the weak links in these materials. However, there's a catch. This had to be done. This wire had to be equal to the price of copper wire that you go and buy in your hardware store. The price of copper wire is $10 per kilowatt meter, which meant that this wire, as I mentioned previously in the hair example that I gave you, you need a critical current density over 1,000,000 amps per centimeter squared. Question was, how do you get it? How do you make a kilometer-long, flexible, single crystal from a ceramic material? Let's ask the first question. What is the largest crystal man has ever grown? So anyway, this became the first holy grail in the field of applied superconductivity. So now if you were to ask the question, what is the largest crystal man has ever grown? The answer to that question is one word, and it is silicon. The largest single crystal grown by man is silicon using the process called the Czochralski process. It is the basis for all microelectronics. The largest crystal really is 18 inches in diameter, about 1.5 meters long. It takes forever to make. It is extremely expensive. Given this, how do you make a single crystal-like material, kilometer long, flexible, at the price of copper wire that you get in the hardware store? This was discounted as fundamentally impossible. Oops. Trying to go forward. Okay, so this is the time where I like to show this YouTube
One of the
video.
things that really hurt Apple was after I left, John Sculley got a very serious disease. It's the disease of thinking that a really great idea is 90% of the work. And that if you just tell all these other people, here's this great idea, then of course they can go off and make it happen. And the problem with that is that there's just a tremendous amount of craftsmanship in between a great idea and a great product. And as you evolve that great idea, it changes and grows. It never comes out like it starts because you learn a lot more as you get into the subtleties of it. And you also find there's tremendous trade-offs that you have to make. There are just certain things you can't make electrons do. There are certain things you can't make plastic do or glass do. And as you get into all these things, designing a product is keeping 5,000 things in your brain, these concepts, and fitting them all together in continuing to push to fit them together in new and different ways to get what you want. And every day you discover something new that is a new problem or a new opportunity to fit these things together a little differently. And it's that process that is the magic. What I've always felt that a team of people doing.
Okay, so now you're probably wondering, what was Steve Jobs talking about here in his video, and how does that relate to what I am talking about? So Steve Jobs was talking about the iPhone, how he created this absolutely beautiful product, right? Now, if you were to just substitute craftsmanship.
One of the things that really.
Sorry, my talk is not advancing. Oh, hang on. Let me see what is. Okay, so if you were to substitute craftsmanship by innovation, our end goal was this high-performance superconducting wire. And just like the iPhone, you go back and forth from the vision back to the drawing board, to the vision, back to the drawing board. That is exactly what we did in the field of high-temperature superconductivity. Our end goal is known. We go to high TRL levels, come back, we encounter all kinds of fundamental challenges. We go back and forth between what we call technology readiness levels to create the impossible. So we realized these wires by manipulating functional defects by the kilometer. We have manipulated grain boundaries, which are two-dimensional planar defects, by the kilometer. We have manipulated one-dimensional linear defects, nanocolumns at nanoscale spacing, by the kilometer. We have manipulated and controlled oxygen point defects by the kilometer. How did we do it? So two processes are being used around the world now to manufacture long lengths of high temperature, high performance superconducting wire. The first is the rolling assisted biaxially textured substrates. This is something we invented at the Oak Ridge National Laboratory. We start with, we call this like an aluminum foil process, much like the aluminum foil you have in your kitchen sink. We just create it out of a different material. We make it such that all the atoms are aligned in all different directions, 3 directions. Then we deposit ceramic materials, which we call buffer layers, on top of them in nanoscale. Then we deposit the superconductor. All of these have the same atomic structure and configuration, which is like a single crystal. Then we deposit some contact layers and then a copper stabilizer layer. The second was a process called IBAD, ion beam assisted deposition, invented by Fujikura in Japan, called IBAD-YSD. They created a textured YSD layer. Stanford invented what's called the IBAD-MgO layer. Los Alamos National Laboratory scaled that up, and then we came up with the final layer called the lanthanum manganate layer, which is put on top of the MgO layer, which is the ion beam assisted layer. And then again, over the superconductor, we have the same silver and the copper. So let me show you in greater detail what these processes are. The rabbits process, we first start with rolling a metal tape of a certain composition. It looks something like this. The rolling is done in a class 1000 clean room. As rolled tapes have a surface finish so that they can take atomic scale deposition of materials. So we start with the metal tape. We roll it to have a certain rolling texture. We then anneal the sheet in a furnace such that when we are done, the 100 plane in the metal is aligned parallel to the surface of the tape, and the 100 direction is aligned along the rolling direction. Then we deposit oxide buffer layers and superconductors on it to have what we call the rabbit substrate. This is just the buffer layers, and the substrate is what we call rabbits. And on top of this, we deposit superconductors. So in the field of thermomechanical processing, which is an old field for over 100 years, it was not deemed possible, or it was not believed that one can create and get a thermomechanical texture which could be so sharp that we remove all high angle boundaries. So it was quite it was quite interesting for them to hear what we had done, where we worked with this is an Euler space. You're looking at the various orientations possible when you roll a piece of metal, an FCC metal, and the two-dimensional pole figures. But we get, after annealing, a near perfect cube texture. So if you had a single crystal of a nickel and you took a 111 pole figure, this is a single peak here, shows the A-axis orientations, and because there's fourfold symmetry in the cubic metal, you get 4 peaks. Here, these same peaks are slightly broadened. You can now, but there are still grain boundaries here, except they're all low angle boundaries. You're looking at now, every pixel here is an electron diffraction pattern. This particular image is created purely from orientation. Like I said, every pixel is an electron diffraction pattern. The image is created by about 100,000 diffraction patterns, and the green boundaries are all less than 5 degrees. So now you can imagine if I had a tape which is a kilometer long, which looked like this, and the superconductor also had orientations less than 5 degrees, I could potentially get very good current transmission. So, well, we just made the metal tape. Now, these are all nickel-based materials. They are very reactive to oxides, and we want oxides. Well, how do we get oxide orientations on a reactive metal without causing detrimental effects? So you're looking at a 100 surface of nickel atoms down the tape. we create what we call a C2x2 surface reconstruction. We put a sulfur atom on every other unit cell. And when we do that, this is what we call reflection high energy electron diffraction patterns. And when we do that, we can deposit oxides on the metal tape with a perfect orientation. Let me explain this a little bit better. So if you look down the surface of the tape, the nickel atoms and the sulfur atom every other unit cell, or in cross-section, and let's say you want to deposit a common oxide called cerium oxide. There's a unit cell of cerium oxide. The first layer that goes down is oxygen. It goes there. Next is cerium. Next is oxygen. And next is cerium. Once you deposit one unit cell, doing the rest of the growth is straightforward and simple. We developed these reel-to-reel systems to demonstrate roll-to-roll deposition, which had never been done before. This is the schematic of the system. We leaked a little bit of H2S gas to automatically create the surface sulfur modification, sulfur atom in every unit cell. We did online Auger to confirm we had the structure. Then we deposited the first buffer layer, the oxide layer. Then we designed additional systems. There's linear sputtering systems that we developed at Oak Ridge to demonstrate that this all can be done. When we created these buffer layer stacks, yttrium oxide, YZ, cerium oxide, and I won't go through this, but here what we do is we try to optimize the buffer layer configurations and the thicknesses to prevent oxygen diffusion. We have yttrium oxide, which reduces oxygen diffusion, so to create avoid a significant oxidation at the metal interface. This is SIMS depth profiling to optimize all of that. So what we have in the rabbits process, we have a metal tape, the composition of which we can choose, create effectively a single crystal out of it. We deposit the oxide layer, the first oxide layer, which gets the right orientation. We deposit a diffusion barrier layer. We deposit a lattice match. That is the rabbits configuration. On top of that, we deposit a superconducting layer. And the atomic configuration is all the same all the way across these layers. We can make these depositions by what we call an in situ deposition process, like pulse laser deposition, sputtering, E-beam, chemical vapor deposition, MOCVD, pulse electron deposition, where the atoms, as deposited, achieve the right orientation. Or we can use what we call an ex situ deposition method, where we take the tape, dip it in a chemical solution, and then take it to high temperature, and that's when the atoms get aligned. Both of these processes work beautifully. So I had showed you in one of the slides previously that this blue curve is what we needed. 3 million amps per centimeter squared, kilometer-long wires. So this blue curve is actually also, we've gotten better. So this is the blue curve starting at 1 million. What we now get for the superconductors and rabbits routinely is 3 million amps per centimeter squared at 77 Kelvin in kilometer-long wires. So this is how we achieve it. If you look at the grain boundaries in the superconductor, in any one of the grain boundaries in the superconductor, this is what it looks like. It is a classic example of a pile of edge dislocations, which you see in textbook, in many textbooks in material science, talking about what is the structure of a low-angle grain boundary. American Superconductor in Boston licensed this technology from us. They had to junk all their $200 million of investment in their first generation superconducting wire, and they created a new factory to make superconducting wires using this method. This is our technology. Then they deposit the superconductor using a solution process. They can make wide superconductors, and then they can slit them mechanically to create these wires. A few of these wires carry more current than all of these copper wires together. Some pictures from their factory. And you can envision how we could potentially make this process rather fast. We can deposit chemical solutions by slot die coating on a moving tape. This is showing you that in just a 34-second residence time, you can create heteroepitaxial oxides. And of course, chemical solution offers very interesting possibilities, which a process like a rabbits process that I just mentioned to you is amenable to. So American Superconductor is really focused on Navy applications. This is some of the materials that are made with this wire, propulsion motors for the Navy, electrical generators for the Navy. Navy is interested in all electric ships, power cables for the Navy, degaussing systems to make ships go invisible. The second process, LMO-enabled IBAT HDS wire. So here's a schematic of this. Superpower is a company in upstate New York. You start with a very strong substrate like a Hastelloy. You first electropolish it, then you deposit some layers to planarize. Then comes the important layer, the ion beam assisted layer, MGO, just a few tens of nanometers, 10 nanometers, and you can get the orientation you need. Here, in this case, the metal substrate has no atomic orientation. And then we deposit the lanthanum manganate layer here, which is a key layer which allows transference of the texture from this layer to the superconductor without detrimental reactions. Here is an example of a 1.2 kilometers long LMO MGO wire. You're looking at the in-plane orientation of the lanthanum magnet layer. Here's another example from another company out in China called Shanghai Superconductor. You're looking at reflection high-energy electron diffraction patterns taken at 1 meter in the length and 731 meters. Very nice and constant substrates can be made, and superconducting wires. Here's another case. This is from Japan, Faraday factory in Japan. Again, they've got the same configuration that I mentioned previously, LMO by sputtering in this case, then they deposit superconductors by PLD. Again, you're looking at the texture of the lanthanum manganate layer over a close to 2.5 kilometer long wire, very constant. So when we had initially demonstrated these technologies in the laboratory scale at Oak Ridge, we thought our work was done. We thought, hey, the Silicon Valley knows how to do deposition. That's what they do. So we went to Silicon Valley to see whether we could work with them. And we found that the only roll-to-roll deposition that went on in the Silicon Valley was to make beer bottle labels at room temperature. No one had ever done high temperature deposition roll-to-roll. So we had developed all of these issues, address all of these issues by research, looking at what happens when you're handling a web at high temperature, tension and deformation of flexible substrates. How do you enter and exit a deposition system? How do you avoid deposition at cold ends, so where you don't get epitaxy in the right orientation? How do you prevent crosstalk in a roll-to-roll web? How do you spool the tape and put interleaves so that there are no reactions? How do you prevent interdiffusion between all these multi-layers? All of this had to be addressed before roll-to-roll deposition and kilometer-long wires could be made. Once we made these wires in kilometer-long lengths, we thought our work was done. But it turns out it wasn't. Why? All high-temperature superconductors, useful superconductors, are called type 2 superconductors. They resemble Swiss cheese. Swiss cheese has holes in it. And type 2 superconductors have magnetic flux lines which go through the superconductor in yellow. If I take one of these yellow lines out and put it here and pass a current in one direction, then there's a Lorentz force in the perpendicular direction which moves this magnetic flux line in this way. If it moves, it destroys superconductivity and creates resistance. So the name of the game was, how can we make these magnetic flux lines going through the superconductor immobile? So, and again, another thought experiment done at IBM. They took a single crystal of a superconductor and bombarded it with heavy ions. And when they did that, they created these amorphous damaged tracks. The ions went through the superconductor, damaged it, and created amorphous tracks, which were nanoscale in diameters and at nanoscale spacing. This is a 50 nanometers here. So when you do that, and you again measure the amount of current you can pass through the superconductor as a function of angle of the magnetic field, when the magnetic field was aligned parallel to these lines, you got this tremendous increase in the amount of current you could carry. The question was, how can you do this in a kilometer-long wire? Oh, and by the way, without adding any cost. Of course, you can't do heavy ion irradiation because that would actually make it'll be very expensive, very slow, and it would make the metal substrate radioactive. That was not an option. So,
Are these defects, are they superconducting defects or are they metallic defects?
these are non-superconducting amorphous defects.
No, amorphous defects.
Yes.
Okay.
So, how do we create this structure? This is the structure that I just showed you. So, in order to address the need, we came up with this innovation. So, when we deposit the superconductor, we automatically create, using a process called simultaneous phase separation and strain-driven self-assembly, essentially the same microstructure, where when you look at the cross-section of the superconductor film, you have nanocolumns. You're looking at Moira fringes here, nanocolumns of, in this case, barium zirconate. And when you look down the film or the C-axis, you see a structure like this. These are nanocolumns of barium zirconate. And now you can start to see this starts to resemble a Swiss cheese microstructure again. These are about 5 to 10 nanometers in diameter and about 5 to 10 nanometers in separation. When you have these nanocolumns, and when you don't have these nanocolumns, at 3 different operating temperatures of 77, 65, and 40 Kelvin, you can see the amount of current you can carry increases dramatically. This is an exponential axis here. And of course, you can change the field orientation, which is important for rotating machinery applications. But in the entire angular range, we can increase the performance of the superconductor. Next, we made these films. We made them very thick. We can make them all the way up to 3 to 5 microns with no microstructural degradation. The nanocolumns start from the interface of the buffer layer. They go all the way to the top. And then we finally have a performance. When we plot, in this case, I'm plotting the amount of supercurrent you can carry per unit width as a function of magnetic field. All these large-scale applications we're talking about, this was published back in 2006, can be enabled if you have such a microstructural modification. So now we transferred this to industry, and worldwide, we make these wires with this nanostructural modification happening on a daily basis. So we understood this process. As I mentioned before, it is a spontaneous phase separation and strain-driven self-assembly process. So one way to study this, we deposit, when we made the films originally, we had put nanoscale barium zirconate inside the superconductor on a single target. We made the film using pulse laser deposition, and we got these nanocolumns. We can understand the strain-driven self-assembly by taking 2 separate targets of the superconductor and the insulating barium zirconate, and we can create individual layers by varying the thickness of the spacer layer. So in this case, we deposit a mixture of the two, and then we deposit a layer of no barium zirconate containing superconductor. And then we can see at what spacer layer thickness do we get alignment. And we find out that when the spacer layer is below a certain thickness, we get aligned nanodots. And hence we get, if we do continuous deposition, we'll get a nanocolumn to minimize the strain. We studied all of this by what we call the modified Cahn-Hilliard equation from a phase separation perspective. Okay, once we understood how this was happening, we can either align the nanorods the way I showed you, or we can modify the strain to align them perpendicular, or we can actually align them in both directions. Again, all of this nanostructural modifications are to increase the performance of the superconducting wire. I won't go through some of this because this goes into a little bit more detail. I'm going to skip some of these slides. But what this allowed us to do for the first time when we had this microstructural modification, first was it allowed us to grow very thick films, which is very important for high current. It allowed us to create isotropic angular dependence, meaning you could apply the magnetic field in any direction you want from 0 to 360, and you could have the same current carrying ability. And it allowed us to create, in addition to the linear defects that I showed you, point defects, which are really important for lower temperature applications. So first benefit, 3 to 5 micron films with no microstructural degradation. I showed you this slide previously. If you didn't have this nanostructural modification, this is what one would get.
Yeah.
Oops, 1 second. My slides. Okay. So if you plot the critical current density versus YBCO superconductor thickness without this nanostructural modifications, you can see that as you grow the film thicker, the critical current density drops. When you have this modification, it doesn't drop. You can make them very thick.
So it's providing stability, mechanical stability and keeping alignment. Is that part of the?
Yes. So that's how you can make thick films.
Yeah.
But of course, so basically it stabilizes the growth.
Yeah, yeah.
Right? But of course, it provides the nanostructural modification that we need for the superconducting application. Second, it allows us to create isotropic angular dependence. And the reason why that happens is when you plot the critical current density as a function of field along two orientations, H parallel to C and H parallel to AB. H parallel to AB is when the field is applied parallel to the superconducting planes in the unit cell. There you get very high intrinsic performance. And when you create this nanostructural modification, we actually get a higher performance than that, even because of that nanostructural modification. But at higher fields, it crosses over and becomes lower. So it crosses over at this point. Now, it turns out that if you pass a current at any other angle, it also goes through here, which means that at any of these points, you get an isotropic dependence, meaning if this is a crossover point, at this point, 74 Kelvin and 4.9 Tesla, we have the same current carrying ability irrespective of the magnetic field orientation. The third very exciting thing happened was that when we cool these materials down to low temperatures, these columnar defects are only supposed to provide us good performance and pinning of the flux line lattice at higher temperatures. It turns out we got at 5 Kelvin a record fraction of the depairing current density for the very first time. Highest performance ever reported originally. And this could only happen if you had a lot of point defects. And there's something called a pinning force. And turns out that the pinning force went to tera-Newton per meter cube, which is absolutely fantastic. So let me just tell you why we get these point defects. It turns out that around each of these nanocolumns, there is still some residual strain, and that residual strain prevents incomplete oxygenation, which results in point defects. So as we increase the amount of these nanocolumns, the transition temperature decreases because we can no longer fully oxygenate the material. The red here is the strain, microstrain modeled by finite elements that we have done. So it turns out that you've got the Swiss cheese microstructure. Now you can draw a circle around each of these nanocolumns where the transition temperature is decreased and you have some oxygen point defects. I won't go through all of these details, but we've actually measured the microstrain locally, and that is plotted here from an individual nanocolumn and a finite element calculation. It peaks somewhere close to the interface, and because of this high density of point defects, we get beautiful pinning at low temperatures. And so we can control the number of nanocolumns, we can control their areal density, and this is now a well-used technology to make the highest performance superconducting wires in long lengths. Here is an example from results from a company called Fujikura in Japan in a 1.4 kilometer long tape showing beautiful performance. And they do this because they've got their deposition chamber using a multi-plume hot wall laser deposition, very isothermal deposition conditions. Here is another example of a different company called Faraday Factory in Japan. Results are presented recently, 1,000 kilometers per year already. not using this technology, they use a different nanotechnology. So today I talked to you about three technologies. The rabbit substrate technology, the LMO-enabled I-batch substrate technology, the flux spinning by simultaneous phase separation and strain-driven self-assembly. Most companies around the world making high-temperature superconducting wire use one or more of these technologies to make that wire. The most exciting thing that has happened in the field of high-temperature superconductivity in the last 5-6 years. It is now recognized that the fastest path to limitless clean energy is by commercial nuclear fusion. Commonwealth Fusion Systems out in Boston, Massachusetts, spun out of MIT Plasma Labs when kilometer-long tapes that I just talked to you about started to be produced commercially and were available to be bought. This entire technology called commercial nuclear fusion is only possible or enabled by these superconducting wires. It is a niche application. Why? Because you need magnetic confinement for which you need very high magnetic fields, which can only be produced by superconducting magnets out to 20 Tesla and 30 Tesla. So this is the vision, to have commercial nuclear fusion in the electric grid. Most billionaires that you can name in the United States are investing in this technology. 1.8 billion in Series B, one of the largest Series B investment ever. Since this company was incorporated, now there are over 30 fusion companies around the world. And these companies are all excited by the possibilities for limitless clean energy. There are no radioactive products, none of that. They are all based on making called magnetic confinement, basically creating a miniature sun inside a magnetic donut. The magnet could be, the configuration could be a tokamak or what's called a stellarator. The amount of wires used in a single tokamak, 20,000 kilometers in a pilot plant, same thing for a stellarator. And the difference between a tokamak and a stellarator, this is what they look like. Superconducting magnets inside and outside contain the plasma, but currents of moving particles, in this case, it's intermittent operation. Stellarator, much more complicated, but it's an axisymmetric magnetic field, continuous operation. Both cases were getting 100 to 150 million degrees centigrade, start simulating the sun, trying to convert hydrogen into helium by fusion, getting a gain over 10, which is the goal. Of course, given the excitement in the fusion field, it is now also creating very significant excitement for wind power, for energy storage. SMES, electric power mandate actually happens, and there's a lot of electrification. You need to charge electric cars en masse, and superconducting magnetic energy storage systems become quite important then. Defense, all-electric planes and all-electric ships, transport, MagLev, industrial applications, all of these technologies that require high-temperature superconducting wires are now suddenly of great interest because magnetic fusion is fueling the need for all of these wires. So with that, let me just mention that in my laboratory here at the university, we have this very unique pulse laser deposition system. It's a laser MBE system. It's a combinatorial system with an ion assist gun, a sputtering gun. We can do layer by layer growth of atoms. We study them using what we call READ, the reflection high energy electron diffraction. We're looking at READ patterns, which tell us the orientation of these atoms. But at the very same time, we can also measure their chemical composition using a process called LAX, low-angle X-ray spectroscopy. When we have both of these together, we can do, along with combinatorial growth, we can have multiple targets. This is a direction of what you call autonomous growth and, MGI, Materials Genome Initiative. All of that is an interest that I have. And more generally speaking, today I spoke to you about superconductors, which has always been my key interest. So in this slide, I've just sort of classified materials based on their electrical conductivity: superconductors, semiconductors, and insulators. So superconductors, what I mentioned to you about today. I talked to you about single crystal-like superconductors in arbitrary lengths and widths. Now you can imagine what would happen in case you were to grow gallium arsenide or silicon or germanium in a similar way. And that is my interest in semiconductors. We've done that. I had a spin out called Tape Solar, which is doing that. And right now, I'm very interested in plastics. Why plastics? Besides electrical energy generation and use, the single biggest contributor to climate change is one word: plastics. And so I lead a center here, the New York State Center for Plastics Recycling Research and Innovation, based on convergent science. And we're trying to hopefully make an impact in the area of plastics. And with that, I'd like to acknowledge the US Department of Energy HTS program over the years. 2-3 decades, the Oak Ridge superconductor team, the U.S. Office of Naval Research, which funds me now, the UB team, and all those who provided me some view graphs that I've used in this talk. And with that, I'd be happy to take any questions, comments, and suggestions. Thank you.
Thanks, Amit. That was a magnificent summary and statement of where we are with this technology. I appreciate that. I have a couple of questions before I turn to the rest of our crew. The superconducting material is a copper oxide, well, yttrium barium copper oxide, right? And which is brittle. And am I correct in thinking that the use of copper or nickel outer layers provides enough mechanical stability for that copper oxide that you don't have to be concerned about mechanical or, in fact, even chemical interactions that would cause it to become unstable in service conditions? How does that all play out?
Right. So given the fact that the superconductor, yttrium barium copper oxide, is a ceramic material, microcracking and macrocracking was a fundamental issue to be addressed.
Right.
It has been completely addressed. The second issue was chemical interactions between all these multiple layers, elements going from the metal substrate to the superconductor during deposition. All of those pieces, all of those things had to be addressed to make this technology work. So taking a look, designing the buffer layers so that there's a diffusion barrier layer, for example, which prevents the diffusion, right? All of those things had to be taken into account. At the end of the day, we're making magnets out of these wires, so they have to be wound. So they have to be wound without degradation in superconducting properties. All of those pieces had to be integrated into this, and that is why I showed this interesting. That's why I like this video from Steve Jobs, because we had to keep going from high TRLs to low TRLs, back and forth. It's sort of this field epitomizes the doctrine of innovation not being a linear progression from fundamental science to higher TRL levels, but a constant back and forth between TRL levels.
Interesting. But you're not concerned about the stability of the copper oxide in these structures when you're putting them into service? They have to be transported. They presumably need to be somehow introduced into these systems. That's not a concern in terms of, for example, fusion energy?
No. So the reason why that's not a concern is on top of the superconductor, there is an electrical contact layer, which is silver. Then there is a copper stabilizer layer. Then the magnet is wound, and the magnet is within a magnet casing. So it is reasonably well protected from the elements.
Right. That was my impression, that the structure was such that it would provide mechanical stability. But I just wanted to know, I guess, be reassured as you have that was part of the wisdom in fact in the assembly.
Indeed.
Okay. And secondly, I'm very curious about the self-assembling nanostructures.
Right.
How did you go about producing them? I guess I missed that part. How did, I know about self-assembling monolayers in terms of chemical adsorption, for example, but how do you produce self-assembled nanostructures? How did that come about?
Okay, so when we had this second sort of, big goal in superconductivity, the holy grail, to create these nanocolumns at nanoscale spacing,
Yeah,
started looking in the field of material science, what had been done previously. So one of the things that we came across was people had done silicon and germanium and had created quantum dots of silicon and germanium, one inside the other. They
yeah,
both grew heteropitaxially. They didn't react that much. They managed to do it. Then there was a paper that came out back in 2004, it was, and we reported these in 2004 as well. Sorry, 2003. Of two oxides, MgO and lanthanum, strontium manganese oxide or something, that when they co-deposited them, they had some evidence of phase separation and nanostructures. So basically, we use those two ideas to say, hey, what are the kinds of materials that we can put inside the superconductor, which will be non-reactive with the superconductor, and
right.
second, which will grow heteropitaxially on the substrate we are growing the superconductor on, and thirdly, also be heteropitaxial with the superconductor. And so when we co-deposit these materials in the laser plume, as the materials go down, they phase separate. But they also like to grow heteropitaxially with each other and on the substrate. And hence, we got this structure.
So, I mean, did you have a sense when you started doing that work that you would produce columns, or are you benefiting from nature and thermodynamics here?
So when we started out, we originally thought that we would get disconnected columns, or
Yeah.
something between the quantum dots alignment that we had seen before in
Yeah.
semiconductors, and in the oxide, one single oxide paper, which wasn't demonstrating everything completely, on MgO and lanthanum-based oxide, we get somewhere there. But I think the very clean structures that we got were clearly the result of starting with a very good target where we worked with nanostructured oxides mixed very nicely into the superconductor, getting a very homogeneous plume. All of that had to happen to create those structures.
Yeah. From my perspective, that looks like the gold standard in terms of producing useful high temperature superconducting devices. I think you really struck on a very important part of technology there. I see some hands, so let me turn on to Eddie and then Albert. Eddie?
Yes, this is going back 50 years, but I was growing monolayer films of aluminum on silicon 111. And one of the things that I found was the enormous temperature and condition sensitivity of how those films grew, and what superstructures actually were created. Because what I saw were uniform surface structures at certain set frequencies, if you will, of the underlying silicon structure, the silicon 111. But it literally, when you were talking about grains, sizes, and so forth, and how they seem to form, it occurred to me that if you get the conditions right, you can very much control that and create perhaps a very uniform structure rather than what seems like a granular hodgepodge of different grain features. I wonder if you've investigated that or what your thoughts are on it.
I'm sorry, I kind of lost you there somewhere. Could you repeat that again?
Yes. back in the day, when I grew aluminum thin submonolayer films on aluminum on silicon 111, I discovered a whole set of different structures that arose out of that epitaxial growth. And as I kept growing the films, basically, I used lead and so forth, and you could actually see the structures growing. And they were very uniform. They were actually very consistent. But it all depended on the temperature of the epitaxy. It depended on pressure within the UHV system that I was using. So basically, what I could do was control what the supercells that grew of the aluminium, which had these grain kind of boundaries, but they were sort of 10, 20 times the dimensions of the silicon 111 epitaxy in which it was growing. So it was actually, it was related to stress relief, essentially. So you could control it very clearly. And I wondered how much work you would put into actually looking at that, at the different parameters that you needed to grow those, to grow your own granular structure.
Right. So everything you mentioned about growth of aluminum on silicon 111, imagine we are doing that at every interface in the multi-layer structure that I mentioned to you.
Yes.
And not just doing it on a static sample, but doing it in a roll-to-roll configuration without wanting to have any change occur along the length. Because if it does, we get a high angle boundary, and that is a problem. So you're absolutely right. Lead, read, you can name all the techniques that you can think about from a deposition in situ tools, as well as all the deposition techniques that you can think of. We have actually tried to play with practically all of these in situ and ex situ deposition techniques in the endeavor to find the best techniques which can give us the best results. So yes, all of this investigation has been done with a very different mindset, meaning we're not talking about a perfectly flat sample, yet we still want what you can get in a single crystal. So just to underline that piece, today the superconductors that we grow by the kilometer almost have better properties than anything that anybody can grow in their laboratory on a perfect single crystal. So to some extent, the statement is often made in superconductor conferences that the silicon technology and microelectronics is very advanced technology. One could argue that what was needed to make superconductors happen is a little bit even higher technology, because we're not talking about a single silicon wafer in a perfect condition having some layers being deposited upon. We're talking about a moving silicon wafer, with some ups and downs, and you got to worry about the temperature, so it's kind of complicated. But yes, all of those issues that you're talking about, how the morphology gets affected, how the orientation gets affected, how the stoichiometry gets affected, strain relief, all of these issues, we've done a lot of fundamental work in this area. We're trying to exploit all of these things like strain. We've tried to exploit as much as we can.
Thank you. Good discussion. I have a comment I want to add to that, but I want to go to Albert first, and then maybe I'll have the final word today. Go ahead, Albert.
Yeah, hi, Amit. Fascinating presentation, but over my head in terms of my domain versus yours. But what I'm gathering from it is your ability to produce superconducting wires will enable a whole bunch of other technologies. And my question on fusion specifically, is that all what they needed? Meaning, if they could have the superconducting cable there is no more other physics that will restrict fusion as an energy source? Do you know?
So here's the thing. The MIT Plasma Lab is a highly reputed laboratory. It's been there for many, many decades. They're smart people, I think. They've done some very nice calculations. So going out, here's the way I look at it. When you get a $1.8 billion investment from a venture capitalist and being the highest Series B, just Series B right now, you know, Series B is a very early investment, right? Of such magnitude. I think the reason they got it was their highest or their biggest risk as presented was the superconductor itself. So they've de-risked the first piece, which is to create a 20 Tesla magnet, which is one of the many magnets which create one tokamak, and they're trying to demonstrate spark. So spark is the first, they call their first prototype to show that they can get a gain, meaning the amount of energy you put into the system and the amount of energy you get out. I believe their goal is to demonstrate a gain greater than 10. Once they demonstrate the gain greater than 10, right? Then of course there's a lot of learning to still be done. Then there's also these issues about there's a high energy neutron that gets generated when you convert the hydrogen atoms to helium, and that can also affect the superconducting property. So everything is not 100% ironed out, but the only way this is going to happen is if the work actually gets done. And I think we're along that line. You're all familiar with ITER. ITER is the world's most expensive experiment, which was designed to demonstrate fusion. It's going to be demonstrated it's being built in Europe, United States. The headquarters are at Oak Ridge for ITER. We've invested many, many billions of dollars, and most advanced countries, Asia, India, China, everybody's invested. But that's made with low temperature superconductors. What the high temperature superconducting wire allowed you to do is to confine the plasma in a small space, thereby decreasing the cost and making it a commercial. The whole concept of commercial nuclear fusion was born because of these superconducting wires. So I am certainly hopeful that the demonstrations that CFS and many other fusion companies around the world are going to make in the next year or so, maybe a few years, couple of years, is going to dictate, and the minute they can show a gain of a factor of 10 or higher, I think they all have plans to go to the next level, which would be the first pilot, for something that can be put online.
But I would think ITER would have used superconducting cables as opposed to the other kind.
No.
They didn't.
So ITER is using superconducting wire. However, they are using what is called low temperature superconducting wire, which is called niobium titanium and things like that. It is the same similar wire which is used in MRI for decades. They do not have high temperature superconducting wire. The difference between low and high temperature superconducting wire is that the operating space of the high temperature superconductor, when you plot the critical current density, magnetic field, and temperature, is very high. Go to very high magnetic fields, and the low temperature superconductors are restricted to a low magnetic field. And so they need a much larger size, many different variables. So that will only be an experiment for science. Because you can go to very high magnetic fields with the high temperature superconductors, that is why all these possibilities exist.
I
Thank you.
believe that the scaling factor for magnetic field, for the size of the facility, goes as a fifth power.
Right.
2 to the fifth power, something like that.
Fourth, I
So
think.
that's why they're able to do what they're doing.
You know, I always promise our speakers that we're going to end by noon, and we're going to end a little later than noon. But Tom, you're going to have the last question today. Go ahead.
Should be very quick to answer.
Okay.
I may have missed it, but did you reach your goal of producing high conducting wire for the price of copper?
Ah,
Right. So that is a very nice and an important question. So currently, I mentioned to you that our original goal was to get it to the price of copper. When that slide was made, the price of copper was $10 per kiloamp meter. However, the world is not the same since it was a few decades back. The price of copper has now increased, and it is increasing. Especially the tariffs are making it increase even more. Okay. So as the price of copper increases and the price of superconducting wire decreases, we're going to come to a happy point. But the point is, right now, I think we are about a few factors higher. So maybe a factor of 5 higher than the price of the $10 per kilowatt meter type number. And so, I think that was the original goal, of course. But of course, copper wire cannot do what superconducting wire does. So I think these are going to merge as any one large scale application takes off. Economies of scale and just innovation in manufacturing, performance gains, all of that. It's really the price performance metric. So that $10 per kilowatt meter number is a price performance metric. If you increase the performance or decrease the price, you get where you want.
very good. Amit, thank you very much for joining us today.
Thank you
You've
for
given
having
us a great overview. We did have Dennis White from the MIT Fusion Lab speak with us at one point several years ago. But this is a great follow-on to that, and I appreciate your taking the time to join us today. We will have another meeting for this season on June 27th. We're going to talk about AI. Don't forget, we've sent around a survey, and so everyone, I hope, will take the time to fill out the survey and get it back tomorrow before the 20th, before next Friday, so we'll have some time to consider how to make the best use of it. But everyone else, have a good day. Amit, thank you so much.
Thank
Take
you.
care, everybody.
Thank you. Bye-bye.
You bet.
Thank you.
Bye-bye.
Amit.